Recorded's rolling. It's Tuesday, May 12th. You guys have your journals out. We were last looking at these journals back on Friday, so it's been a few days, but we're picking up here number 22, superconductivity, which is also going to lead right into number 23, quantum locking. Here, actually, superconductivity, let's do the graph with you guys right now. So the story goes, um, scientists go back over 100 years ago, really, where looking at the resistivity of materials as a function of temperature. Okay? So let's put temperature in Kelvin on this horizontal axis. So make this, say, the independent variable. Okay. I'm going to start maybe room temperature and they go colder, colder, colder. Now, absolute zero is 0 Kelvin. So we have zero here. Okay. And then if you are either looking at the resistance in a wire, or do you guys remember that Play-Doh lab? I had you guys take try the resistivity of that material Play-Doh a few weeks ago. You remember that? So let's do it from that perspective. We'll look at resistivity. So it's more of a material type property. This could be in ohm meters, right? Okay. Right. And then they noticed as the temperature changed, what do you think, guys? If you make a wire colder and colder and colder, do you think that makes it easier or harder for an electric current to pass through? Harder. Yeah. So it turns out that cold materials transmit electricity better than warm materials. So they were watching the resistance of the wire, therefore the resistivity of the material decrease, decrease, decrease. Okay. And you can try different materials, you try aluminum or copper or whatever, and they'll tend to follow this type pattern, right? Until there was some critical temperature, I'll call it T sub C for some critical temperature, where all of a sudden the resistivity of the material plummeted to zero, pretty much. Okay. And that's what this is right here. This zero resistivity part where it's super cold. Okay. Might be just a degree or two above absolute zero. That's a superconductive. Okay. And if you have a material that's superconductive, then one thing you could possibly do is loop the current in on itself. So you have some current measured in amps, right? And it'll never actually lose any energy, right? So they store energy like a battery that way. There's some other interesting things you can do potentially with superconductivity. So you got some graphs. Uh, okay. So I don't know why this one's showing up kind of fuzzy, but well, okay. Yeah, you can see here. So resistivity is a function of temperature. Okay, yeah, so this one goes down to looks like about 90 something Kelvin, 90 Kelvin, right? For whatever material this was. It went superconducted there, and there's basically no resistivity. Right? Now different materials oh no, it's getting all messed up here. Well, let me see if I can open this in paint, possibly. Open with okay, maybe a little better. Let's see what this looks like. Okay. Okay. So, um, okay, year by year, different materials that were found to go superconductive and what critical temperature. So it looks like all the way at the beginning here in the 1900s, it looks like mercury, that's what Hg is. Right, okay, and then lead, that's what Pb is. Right, those are maybe some of the first couple that were found to go superconductive. Have to be really, really cold, like less than 10 Kelvin. You guys see that? So it's getting really close to absolute zero. They'll go superconductive. Right? And then these other materials closer to room temperature. But no material has been found to go superconductive at room temperature yet. That would be really huge technology, but looks like the warmest they got here is 200 Kelvin, which is still crazy, crazy cold. That's like Antarctica level cold. Okay? But the catch is, even for this one, is you do also have to have a high pressure to make that work. So that's like that. All right, so what's something interesting you can do with superconductivity? Okay. And I got for you guys quantum locking.
The phenomenon you saw here for a brief moment is called quantum levitation and quantum locking. And the object that was levitating here is called a superconductor. Superconductivity is a quantum state of the matter, and it occurs only below a certain critical temperature. Now, it's quite an old phenomenon. It was discovered 100 years ago. However, only recently, due to several technological advancements, we are now able to demonstrate to you quantum levitation and quantum locking. So, a superconductor is defined by two properties. The first is zero electrical resistance, and the second is the expulsion of magnetic field from the interior of the superconductor. That sounds complicated, right? But what is electrical resistance? So electricity is the flow of electrons inside the material. And these electrons, while flowing, they collide with the atoms. And in these collisions, they lose a certain amount of energy. And they dissipate this energy in the form of heat. And you know that effect. However, inside a superconductor, there are no collisions. So there is no energy dissipation. It's quite remarkable. Think about it. In classical physics, there is always some friction, some energy loss, but not here, because it is a quantum effect. But that's not all, because superconductors don't like magnetic fields. So a superconductor will try to expel magnetic fields from the inside. And it has the means to do that by circulating current. Now, the combination of both effects, the expulsion of magnetic field and zero electrical resistance, is exactly a superconductor. But the picture isn't always perfect, as we all know, and sometimes strands of magnetic field remain inside the superconductor. Now, under proper conditions, which we have here, these strands of magnetic field can be trapped inside the superconductor. And these strands of magnetic field inside the superconductor, they come in discrete quantities. Why? Because it is a quantum phenomenon, it's quantum physics. And it turns out that they behave like quantum particles. In this movie here, you can see how they flow one by one discretely. This is strands of magnetic field. These are not particles, but they behave like particles. So this is why we call this effect quantum levitation and quantum locking. But what happens to the superconductor when we put it inside a magnetic field? Well, first there are strands of magnetic field left inside, but now the superconductor doesn't like them moving around because their movement dissipate energy, which breaks the superconductivity state. So what it actually does, it locks these strands, which are called fluxons, and it locks these fluxons in place. And by doing that, what it actually does is locking itself in place. Why? Because any movement of the superconductor will change their place, will change their configuration. So we get quantum locking. And let me show you how this works. I have here a superconductor, which I wrapped up so it stays cold long enough. And when I place it on top of a regular magnet, it just stays locked in midair. Now, this is not just levitation, it's not just repulsion. I can rearrange the fluxons and it will be locked in this new configuration, like this, or move it slightly to the right or to the left. So this is quantum locking, actually locking, three-dimensional locking of the superconductor. Now, of course, I can turn it upside down and it will remain locked. Now that we understand that this levitation, so-called levitation, is actually locking, yeah, we understand that. You won't be surprised to hear that if I take this circular magnet, in which the magnetic field is the same all around, the superconductor will be able to freely rotate around the axis of the magnet. Why? Because as long as it rotates, the locking is maintained. You see, I can adjust and I can rotate the superconductor. We have frictionless motion. It is still levitating, but can move freely all around. So we have quantum locking and we can levitate it on top of this magnet. But how many fluxons, how many magnetic strands are there in a single disk like this? Well, we can calculate it, and it turns out quite a lot. 100 billion strands of magnetic field inside this 3-inch disk. But that's not the amazing part yet, because there is something I haven't told you yet. And and the amazing part is that this superconductor that you see here is only half a micron thick. It's extremely thin. And this extremely thin layer is able to levitate more than 70,000 times its own weight. It's a remarkable effect. It's very strong. Now, I can extend this circular magnet and make whatever track I want. For example, I can make a large circular rail here. And when I place the superconducting disk on top of this rail, it moves freely. And again, that's not all. I can adjust its position like this and rotate, and it freely moves in this new position. And I can even try a new thing. Let's try it for the first time. I can take this disk and put it here. And while it stays here, don't move, I will try to rotate the track. And hopefully, if I did it correctly, it stays suspended.
Pretty cool right there. All right, so here's my poster versions of these. All right, so there's your superconductivity, and there's your magnetic field fluxons for quantum locking. What it could look like. Actually, let me roll a real short one, and then flip over and give you guys some notes. All right, a little bit different topic here.
To make a laser, all you need to do is give a big collection of atoms enough energy so they're excited and ready to emit light. Once one of them spontaneously emits a photon, it'll stimulate some of the others to do so, and you get a nice cascade of illumination. But instead of letting all the light escape, it's more powerful to trap it between two mirrors and let it bounce back and forth through the atoms. All that passing light will stimulate them to emit even more light, and as long as you keep on re-exciting the atoms, they're happy to go on emitting light forever. But why do the atoms emit light just because another photon passes by? It's actually pretty simple. Imagine flipping two coins. They can either be in the same state or in different states. But photons aren't like coins. No matter how hard you try, you can't tell one apart from another. So in a photon flipping experiment, that means there's only one way for them to be in different states, but two ways for them to be in the same state. So they're more likely to be in the same state. And in general, this implies that photons always want to be like other photons, to have the same phase, polarization, and go in the same direction. And what's more amazing is that if a solitary photon passes by an excited atom that could emit another photon, there's a good chance it will emit one, because the two photons want to be together, even before the second one exists. So once you have all these friendly photons bouncing around between the mirrors, you can just open up a little hole at the end and let out a blinding stream of coherent light. A laser beam.
This next one, how lasers work. That's a good stuff right here. That's it's all the talk about quantum locking. That's this superconductive material. You guys saw that look like white clouds of smoke leaving it. Guys, what was that? What was all that white clouds of smoke leaving the superconductor?
Nitrogen.
Yeah, almost certainly so. Almost it was liquid nitrogen that was going and warming to gas form. Right? Because you had to have it super cold. Right? That's one feature to make these superconductors work. Right? And then you put this in a magnetic field. right, which has these quantized magnetic field lines called fluxons, right? And then some of them get stuck in the superconductor and most those are expelled. Right? And then it can stay locked in place in some relative position, right? And that's where you, well, right, cut off this video, we had it like going on a ring upside down with Valkyrie. Right? Okay, and then here's that short follow-up video you guys saw, which was how do lasers work? Okay, so there's this quantum explanation of photons are not readily distinguishable in a quantum sense, right? What is a particle? What is a wave? Right? So if you get these photons of light reflecting back and forth between these mirrors, then they'll, from a quantum perspective, more likely have the same polarization and be in phase. Right? So those individual photons of light are not readily distinguishable.
Atoms are a bit like people. They're very hard to predict with absolute certainty. They do roughly what you would expect of them, but never exactly. With atoms, it's even hard to be totally certain whether they exist or not. Sometimes, Hawking knew, atoms pop up when there should be absolutely nothing around. In fact, out in space, it's happening all the time. The theory of the very tiny says space is never empty. At an atomic level, there is always a tiny, tiny amount of activity. But the theory of the very big says nothing exists at the edge of a black hole. Hawking realized this was where the two theories clashed. He had to find out what was really going on. According to the theory of the very tiny, in empty space, there are pairs of subatomic particles that emerge out of the void, exist for a tiny moment, and then destroy each other.
And so the idea is that out of nothing, if you like, a pair of particles is created and then exists for a short time and then annihilates. And that's happening throughout space. So it's happening there, and it's happening there, it's happening there.
This pair of particles is like yin and yang, night and day, opposites that would not exist without each other. One has positive mass and the other has negative mass. But Hawking asked, what would happen if this pair of particles bumped up against a black hole? Hawking realized that the positive particle would have just enough energy to escape the black hole, but the particle with negative mass would fall in. And it would do something extraordinary to the black hole.
Particle that goes inside the black hole eventually decreases the mass of the black hole. It effectively has negative mass, but the particle that goes off to the distant observer is there observed as part of radiation.
Although we now understand why black holes have to give off thermal radiation, it came as a complete surprise at the time. At first, I thought I must have made a mistake.
But Hawking had not made a mistake. Around a black hole is an almost imperceptible microscopic glow. Positive mass particles fly off from it, behaving just like heat. Negative mass particles fall in. Slowly, almost imperceptibly, they decrease the mass of the black hole, and this eventually has catastrophic consequences.
So, what the Hawking result implies, it means that the black hole, instead of being black, is actually always emitting radiation. What is happening is that for most of its life, the black hole is gently sizzling away, but eventually it gets smaller and smaller, the temperature gets hotter and hotter, and eventually it gets to a point where it's so hot that it essentially explodes. It loses all the rest of its mass in a very, very short time.
Hawking had transformed the black hole from a ball of nothing into a galactic monster that chews up the universe and spits out fire and brimstone.
When black holes were first thought of, and when I first started studying black holes, even I remember thinking, oh, a black hole, it's the end of everything. A star collapses down and everything disappears into it and nothing ever comes out. So maybe it's really boring. But really, black holes represent our best way to have an ultimate test of the physics of understanding the universe.
All right, here, main gist of that there. All right, so the idea is, if you go back to Newtonian perspective of the world, right, things exist or they don't, right, pretty straightforward. But from a quantum perspective, well, all over the universe, you have spontaneously popping up these particle-antiparticle pairs. Now, normally they just immediately annihilate, so as if they were never there, it makes no difference. Okay? But the interesting test here is, what if you take this process and put it near the edge of a black hole where not even light can escape? Okay? And it is that if you run the math on this, you could run into some situations where sometimes the antiparticle will fall into the black hole, but the particle that appears with it can have enough information to escape the black hole. Okay? And in that situation, the particles is escaping and going to a wider universe. That's what you can detect as this Hawking radiation. Okay? So you can observe that. Okay? And then, of course, there's this other half of the story. But if you have on net a bunch of antiparticles falling into the black hole, right, that would be annihilating the matter that's already there. Right? So run the clock forward enough time, and then eventually the black hole will dissipate. That whole interesting story going on right there.
The normal background radiation sounds like this. But this rock is a little more interesting.
Got a Geiger counter.
And it's this rock which turned out to be the clock which allowed us to date the Earth.
The rock contains uranium, an element that loses subatomic particles over time. Those losses change uranium into other elements with fewer particles. It's a process known as radioactive decay.
If you leave uranium around for years, it all turns into lead. But it turns into lead a little bit at a time. So you can measure the rate at which it turns into lead. Once you know this rate, which is not hard to figure out physically by watching the process happen in real time, you can go to a rock sample, break it open, and measure the relative amounts of different kinds of lead and uranium in it, and determine from this how long it's been since the rock cooled.
This was a phenomenal discovery. And in the very earliest, most simple attempts at it, it was discovered that, in fact, the Earth had to be an order of magnitude older than previous estimates had argued for. And the average looked like was about 2.5 billion years at that time.
Ultimately, rocks are found that are 4.5 billion years old.
You guys catch that detail right at the end? Okay, so rocks have been found that are 4.5 billion years old. Okay, if you're ever asked what's the age of the Earth, or if that shows up, yeah, that's kind of the scientific consensus right now, is that the Earth is 4.5 billion years old. How do they know that? Because of this chart right here, and because of a process called uranium lead dating. So some atoms are radioactive and many are not, okay? But everything along this chain is until you get to lead at the bottom. Okay, see this lead, right? And there's all different half-lives along this process. So to go from, looks like uranium to thorium takes, says 0.71 gigayears. So, right, giga is like billions of years, right? And then from thorium to, I think it's palladium here. So what is that, 25 hours, right? Okay, and then this half-life looks like 32,000 years, right? Some of these are days, some of these are seconds, milliseconds here. Now when we get to lead, lead is no longer radioactive, that's stable. So if you pick up like a freshly created rock of, say, uranium, then it's going to be 100% uranium. You say, okay, well, this came out of, however uranium's created, maybe either a supernova explosion or, there's different ways for elements to be created. Right? Maybe this was created yesterday. Now, if it has some lead in it, and you know all these half-lives of this whole chain process, and you know the proportion of lead to uranium, you can calculate the age of the rock. There's a whole interesting history story behind this too. Here's the scientist who originally did this. His name was Claire Patterson. And when he was going about this process, he realized he had to get rid of all the lead contamination in the environment of his laboratory to be able to get accurate calculations for the ages of the rocks and eventually figure out the age of the Earth. Yeah, through that process, he realized that there was lead all over the place that had been put there by, well, humans through burning gasoline in cars. Right? That's why, like, to this day, if you go to the gasoline pump and it says this gasoline is unleaded, and then there's like super unleaded, but it's all some version of unleaded. Why were we getting rid of the lead in the first place? Because he realized that we were lead poisoning the entire planet, and that had lots of bad repercussions too. Right? It's bad for people's health and so on. Right, so, all right, so actually, what I got, let me play one more for you guys before I give you guys some notes here. Let's look at a specific kind of carbon-14.
Carbon is a critical ingredient for life on Earth. Living things are made up of about 25% carbon. The carbon atom is unique because it can bind to other carbon atoms to form long chains and rings. And these in turn serve as the backbone of complex molecules that make life possible. The nucleus of a typical carbon atom has 6 protons and 6 neutrons. But about 1 carbon atom out of every 100 has 1 extra neutron. This has very little effect on the properties of the carbon other than making it slightly heavier. Chemically, it acts just like any other carbon atom. It is called carbon-13. And there's an even rarer type of carbon. It is formed high in the atmosphere when cosmic rays strike atoms of nitrogen, converting them into carbon-14. Carbon-14 is also chemically identical to regular carbon. But the nucleus of carbon-14 is unstable. After some amount of time, which could range from a few days to many thousands of years, carbon-14 decays back into nitrogen. But since carbon-14 is formed at a steady rate, there is a constant level of it in the environment. Out of every trillion carbon atoms in your body, only 1 dozen of them are carbon-14. As long as an organism is alive and eating, it maintains a constant ratio of carbon-14 to regular carbon. But once the organism dies, the amount of carbon-14 in the body begins to decrease. After 5,000 years, about half of the original number of carbon-14 atoms will have decayed. Using this fact, scientists can tell how long ago an organism died.
All right. So here, I'll put this graph together with you guys. So we're looking at, in general, radioactive dating, but one version of it is carbon-14. Now, if you use uranium and lead, you can count that potentially billions of years, right? So how you say the Earth is 4.5 billion years old. Okay? Now, this carbon-14 method is a lot more, well, okay, maybe can only go back like thousands of years. Okay? You guys can see this here. So let's make a graph here. Make a graph. Okay. So I'm going to put time on the horizontal axis, so time's ticking by. And I'll call this like amount. Let's like maybe it could be a concentration of carbon-14, right? If you're talking about some organic tissue, organic material, okay? And at time 0, maybe there's some initial amount. I'll call it A naught, or something like that, right? Okay. So outlet. Okay. Well, different radioactive materials have different half-lives, okay? And for carbon-14, that half-life happens to be 5,730 years. So let's put on this axis here, 5,730 of time. I'll put years. Right? We're talking about years in this case for carbon-14. Okay, you guys, if the half-life of carbon-14 is 5,700 some years, what does that mean? That means after 5,700 some years, we have how much of the carbon-14 remaining? Half. Yeah. So we're down to half of however much we started with. So at time 0, we had some amount. And then after one half-life, we have half of what we started with. Okay, well, if you zoom forward another half-life, what would that be? Is that 11,460, I think, years from time 0? Right. You guys see that would be 2 half-lives, right? Okay. Guess how much we have at that point compared to what we started with? Quarter. Yeah, a quarter. Okay. Because we have half of a half. Is it? Okay. And if I go forward another half-life, I think we're up to 16, 17,000 years, something like that. Okay, now we got an eighth of what we got. So like half of a half of a half. Right? And you guys see this process could mathematically just keep going on and asymptotically approach 0. Okay. Now, when you use this to carbon date objects, you can go back and it gets kind of fuzzy, but about 50,000 years, and then anything older than that, this process isn't super accurate anymore. But you can carbon date something quite a lot of that. Now, to give you guys a couple numbers. So carbon-14 half-life, so T sub 1/2 half-life is 5,730 years. Okay, so it looks like this graph is specifically for carbon-14. Okay. Now, I'm going to give you guys a couple of formulas that can both describe this curve, right? Some general formulas. The more intuitive formula is the amount as a function of time is equal to the initial amount times, and then you guys notice that all these points that I plotted, it's like, well, it's half and then half and then half. So we'll say 1/2 to the power of the amount of time that's passed divided by the number of years in a half-life. Okay. So 5,700 years have passed, and 5,700 years is also one half-life. This whole exponent is equal to 1. And then I take the initial amount multiplied by a half one time, and I get down to this point here. Okay. If 11,000 years have passed, say 11,000 over 5,700. Okay, so now this exponent is equal to 2. Okay, so now we're doing 1/2 squared, so it's like half of a half. That gives me this point right here. Okay. If you get a multiple of 3 half-lives, this exponent is 3, and so on. You guys see it? Okay. Now that's the more intuitive version of the formula, I think. I'm going to give you guys both these formulas because I remember when I tutored math back in college, students would get like both perspectives of these. So go to college, you might see both of these. Okay? The more mathematically pure version of this, though, let me give you guys a different version of this. Same formula could describe the same curve, but I'm going to change this base value. Okay, so yeah, we're starting off with some initial amount, so that part's the same. Okay. Actually, some of you guys might know what I'm about to write, especially if you're taking my algebra class. Okay. Guys, I'm not going to use the base of 1/2. What base do mathematicians really, really, really like? E. Yeah, it is. It's E. Okay. And then, okay, but now that messes the whole exponent up. So I'm going to say e to the power of kt. If you know it's going to be an exponential decay, sometimes you automatically put a negative value there. If you don't, the k itself will be negative. Right? Yeah, e. And guys, what is e? What is e? Is that a special number? Yeah. Kind of like pi. Like I said, what is pi? You say, oh, it's 3.14, blah, 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 blah. Okay. How about this? It's on your calculator. Hit second if you have this model calculator. And then see this key, it says ln for natural log. Hit that. But if you hit second first, it'll say e to the power of. Now if you put 1 there and close that, e to the power of 1 would be e, wouldn't it? Okay. I bet some of you guys know what number is going to pop up when I hit enter. What's the number? 2.718, something. Right. Now, this is an irrational number, so kind of like pi, it continues forever with non-repeating digits. Yeah, so it's irrational. So it's so a special number in math has some interesting properties. You see it show up at quite a few places, and we're going to use it in this exponential growth and decay curve too. Okay, but if you want to use it in the formula, you do have to figure out what is k, as it associated with some particular half-life of some radioactive element. Okay. Okay. Guys, let's do this. You should have the backside of your journal should be blank. Let's do some calculations here. We're gonna do calculations on the back of your journal. Okay, guys, ready for this? Okay. So here's the premise: is that you're an archaeologist. Okay, you are an archaeologist. Yeah. And let's say you find an artifact that has, all right, let's say you take it to the lab and it has, let's say 23% of its original carbon-14. Okay, and the question is, how old is the artifact? Or maybe find a few artifacts and they're all about that. Okay, yeah, it looks like pretty consistently this whole dig site, we're finding these organic artifacts that have 23% of the carbon-14 they would have if they were actually alive or had like the day they died. Okay? Okay. And it could be any organic material. So it could be cloth or paper, right? Those come from plants also. Right? So chop down the tree or kill the linen or whatever plant you got this from. Right, so you guys this? So everybody got this so far? Right, we're gonna find out how old. Okay. Now, before I go chugging and plugging on the map, let's get kind of an estimate first, so that when we actually get an answer, we'll know. Okay, yeah, this does make sense. Okay, it's 23%. Now I just made up that number from scratch right now, but what fraction does that look really, really close to? But not exactly. Yeah, 1/4. Okay, that's what I'm trying to get. Okay, so this is fairly close to a quarter. Very close to a quarter. And then if you look back at that graph I just had you guys draw, okay, if something has a quarter of the original value, how many half-lives should that correspond to? 2. Yeah, it should be 2 half-lives. And since you know 1 half-life for carbon-14 is about 5,700 years, do you guys think that the artifact that we just uncovered here is maybe about 11, 12,000 years oldish, somewhere there? I'm going to guess about 12,000 years, something like that. Okay. But let's figure out more exactly. So first thing, we got to chase down that k value from the exponent. Let's use a base of e. We're going to use a base of e, just like an actual mathematician here. So let's go. The amount is equal to the initial amount times e to the kt. Okay. And first we got to solve for k. Now that k is going to be true for carbon-14, regardless of how old is the artifact. Okay. I'm gonna see if you guys can apply a little bit of creativity here, and especially if you've been taking my algebra class, you might have a head start on this to be able to figure this out more quickly. Okay? Is how can you solve for k? Can you guys think of a creative way to solve for K for this scenario? Okay, yeah. It's important we're gonna have to use the natural log. I do need to plug in some numbers at some point. Right? Because how about this? If you did plug in the half-life value, which is 5,730 years, what would you expect to be the relationship between A versus A naught? If we let exactly one half-life be plugged in. Shouldn't we have half of what we started with? Wouldn't that be true? Right? Now, at this point, you can make up anything for A naught. You can say, I start off with 100 units. And if I plug in 5,730 years for time, this is years, okay, then I should end up with how much right here? If one half-life is passed, which means we have how much? Because what's half of 100? 50. Okay. Now I just made up 100 as in maybe 100 units or 100% or whatever. Okay? Because I could put any number here, and if I plug in one half-life worth of time, then shouldn't I always end up with half of what I started with? Okay. Here, let me either reduce this to the next algebra step or maybe start over, however you like to think of it. Okay. If I start off with any amount, I'm always going to end up with half of that original amount, as long as I plug in one half-life worth of time, which I did, 5,730 years. You guys get it? Okay. All right, so that's okay, right? Okay. Okay. I hope you guys get that concept. I bet a lot of you guys, maybe everybody here is going to be taking a college class one day, and you're going to run into this scenario, and you're going to have to figure that out. Okay. And then, Jan, you said to apply to what? Natural log. Natural log. Let's do that. Right. Natural log both sides. Okay. If you're taking my algebra class, I know you've seen this. And how about anybody else? Have you guys seen this process of applying a natural log? The idea is like what you're trying to solve for, right? If this step is stuck in the exponent. So if you want to bring it out of the exponent, you have to apply logarithms. And yeah, we're going to do natural log both sides. So that this natural log of e just goes away here. Let me show you guys that's true. If I take natural log of e, that's just equal to 1. Right? There's a few ways to think about this. But what used to be power is no longer a power. Now it's down here. Now I can solve for k. I can say it's very simply natural log of a half over 5,730 years. Okay. Now this is the exact answer. Let me say approximately equal to. Let's get a decimal approximation. What is natural log of 0.5? Whoops. Natural log of 0.5, and then close parenthesis divide by 5730. That's that looks right. Negative 0.000121. And the unit is 1 over years. Okay, so there's k. Okay. Now that doesn't solve yet how old is this artifact we found, but we're halfway there. Okay, you guys good? Good. Okay. So this is true for carbon-14. Okay. If you ever run into a problem one day and you're given carbon-14. I mean, if you happen to memorize this, then this is the k value that corresponds to this equation with the base of d and the whole thing, right? Okay, now let's go back to this 23%. All right, you guys ready to plug in 23%? Okay, so we'll set up a new equation. We'll say, well, the amount we have is 23% of something that started at 100%. I'll say times e to the power of, now I have a value for k, negative 0.000121, 1 over years. Okay. But now I'm solving for time. Isn't that the goal to figure out how old is this artifact? Right? So let's do it. 23 over 100. That's 0.23. And I'll take the natural log of both sides here. I'm going to skip an algebra step. So we take the natural log of both sides. And then on the right side, that just gives me negative 0.000121t. Okay, solve for t. I'll divide by this coefficient, which looks like that k value that we found from before. Actually, I've got it stored on my calculator screen, so I'll just say divide by input. So it's natural log of 0.23 divided by, so that crazy value that I have plugged in right there. Okay. Now, guys, remember before I started on any of this math, I had you guys come up with an estimate for how much time it passed for this particular artifact with 23% of its original carbon-14. And you guys said it should be approximately how old? Yeah, wasn't it just a little more than 2 half-lives? So I bet it's going to be somewhere between 11,000 and 12,000 years. Do you think between 11 and 12,000 years? Let's see. We're about to find out. Oh, okay, actually a little more than 12,000. Right, it's even kind of older than I was looking for. Yeah, that's like right in there. I mean, that was believable. 12,000 years, 12,149 years. Right. So that's how old this artifact is. Right. Great. And you guys just carbon dated an old artifact. You guys are well on your way to become archaeologists. All right, you guys get there. You guys get there. All right. You guys got all those notes. All right, so tell you what, since we just got a couple minutes of class left, do you guys know what unification is? Okay, so at this point in this class, we have these conflicting laws of physics. Right, there's general relativity, which is kind of overtook Newtonian mechanics. That's like macro scale. It's what we've been doing this entire year, starting in August all the way up to through relativity. Okay, and then the past week we've been looking at quantum mechanics, and you got all these weird laws. You get Schrodinger wave equation, you get collapsible wave function, double slit experiment, Heisenberg uncertainty, and all these crazy concepts that never seem to show up very well in macro. Right? So there's this open question of, can you unify these two seemingly conflicting laws of physics to answer questions that we can't answer otherwise, like what is going on either inside or at the edge of a black hole, or what happened at the beginning of the universe, or come up with like some master laws of physics. Right? One proposal for this is something called string theory, where maybe everything's made of tiny vibrating strings that are way too small to see or detect. There's something else called quantum gravity. There are some competing ideas, but things that are difficult to really test scientifically. And then if we ever master physics at this level, could you apply technology to this? Right? So could you maybe one day, possibly in our lives, I don't know, we'll see, have some idea of something that you want in your mind, and like have a magic box, and you press a button and it rearranges molecules and makes like anything you want, right? Which would probably take a lot of energy, but that might be a possible technology. Okay, but yeah, let's just go ahead and skip those. You guys double check, make sure your name's on your journal. Is your name on your journal? Go ahead and turn this into the grade tray, and as long as you have everything that we covered, I'll give you credit for those. If you think you missed something, then you can turn it in tomorrow. That's right, too. That's our wrap on quantum.